For the last few classes we were having, theoretical discussions because I wanted to progress, and anyway we are having a tutorial in the evening, so I thought that maybe we can start some numericals. That also saves me the time to prepare another set of notes. So easy, I had to prepare for the tutorial probably more than what you have to prepare for the tutorial. So okay, so I did the same thing as probably what you are doing. So I picked up some problems. Some of them I could solve, some of them I found difficult to solve. So I said, just like everybody else, I thought, okay, I'll get back to these hard problems later, just like everybody else does. So I have solved some. So I thought that I can share what I have solved with you, right? So the first problem, this problem was somewhat simple. Just see whether you can make out what is happening here. So the problem says that let there be two coins, right? One is fair. Fair means that the probability of getting a head and the probability of getting a tail is same and is equal to 0.5. That's called a fair coin. And the other is two-headed. It's like that Sholay movie coin, So both sides are head, right? So a coin is picked at random and tossed twice. So there are two events here. One is picking up the coin among the two, and the other is tossing it twice, right? Heads shows both times. So when you toss them twice in a given experiment, you got heads both times. Given that heads showed both times, find the probability that the picked coin is fair. It's the other way, right? So this is a case where you are, what is the probability, what is the general probability that the picked coin is fair? It is half, because you are picking up one of the two coins and you are picking it up in random. So the probability of picking up the fair coin is equal to the probability of picking up the two-headed coin. So the a priori probability of picking up the fair coin is 0.5, but you are given now you are given a fact. It is not the a priori probability that you are calculating. You are given a prior information that both times it showed heads. Now what is the probability that the picked up coin is fair? So the probability is going to be different, right? So we will apply what? We will apply Bayes' law, right? So let us first mark the events, okay? So let A be the event that the fair coin is picked. And let B be the event that heads show both times. Alright. So what are we trying to calculate? We are trying to calculate probability of A given B. This is what we have to calculate. right? So what is probability of A given B? It is probability of B given A into probability of A divided by probability of B. Right? Now what is probability of B? Why?
Half, and first probability is that head comes is half. Again, second time when the
That is if the fair coin is picked.
Yes.
Probability of B means
Yes, is exclusive.
no.
Probability of B event we have defined that head shows both times.
Right, head show both times. What is the probability irrespective of which coin is picked?
Yes.
So irrespective of which coin is picked, head show both times probability is not half. Is not. If the fair coin is picked, then the probability is 0.25. Not otherwise. So this is actually probability of B given, let us say, suppose A bar is the event that the fair coin is not picked. I am having difficulties writing, so please excuse, as such my writing is not great. Into probability of A plus probability of B given A bar into probability of A bar. This is the overall probability of B, irrespective of which one is chosen. So either A is chosen, either A occurs or A bar occurs. So if A occurs, then what is the probability, and then if A bar occurs, then what is the probability? Taking them together, you will get the probability that either A or A bar occurs. And then what is the then top remains the same. All right. Now you put values. So this is what you are saying, 0.25. Probability of B given A, that is 0.25 into what is probability of A? Half divided by this is the same, so it is 0.25 into 0.5 plus what is probability of B given A bar? It is 1. So it is just 0.5. So it is 0.25 by 1.25 is equal to 0.2. So what you are effectively saying is that if you see both heads coming up, then there is a much higher probability that the coin that you have picked is actually the two-headed one, because the probability that you have picked the fair coin and you got two heads is actually rather low, right? So this is one of the, see, otherwise, I mean, if you don't apply Bayes' law, then this problem appears somewhat, confusing. That, I mean, how do you are asking kind of the reverse question. We are more used to the fact that if the coin is fair, what is the probability of getting two heads? We are generally more used to this. That's more simple to imagine. But here we are asking the reverse question. Given two heads, what is the probability that the coin is fair? And using Bayes' law, now we have inverted the conditionalities, right? So I hope this is clear. This probably you could anyway do it. It was a simple problem. Now let me complicate this problem a little further. Okay, this is also a nice problem which uses the same kind of Bayes rule but for a different application. This says that the probability of heads of a random coin is a random variable p. Now we are having many coins, some of them are unfair coins. What is meant by unfair coin? That means the the probability of getting one event is actually larger than the other, right? And sometimes used by gamblers. Gamblers will use this kind of thing so that they will change the mass distribution or something that, and they will toss it in a clever way such that always the probability of a tail coming up will be higher. Okay, such a coin is called an unfair coin. So in general, you can imagine it is very difficult to have coins which will have 0.9 and 0.1 probabilities and still look like a coin. That is rather difficult to construct probably, but for the sake of mathematics, let us imagine that there could be a coin in which this probability of having a head can vary anywhere between 0 and 1. Okay, so it is a random variable. You pick a coin, you get a probability, that sort of thing. If a coin is chosen at random, now you are choosing a coin at random and toss 10 times and heads show 6 times, find the probability that this value p for the chosen coin lies between 0.3 and 0.7. That is a little more complicated, isn't it? So how do you do it? Again, we'll again. So what is the again first mark events? Okay. So first mark events is A is the chosen coin has P this is the first event, and the second event is 6 heads in 10 tosses. Right. Now, what are we supposed to find out? We are supposed to find out probability of A given B. This is what we are supposed to find out. See, in the previous problem, this P function was actually discrete. It was either 1 or 0.5. P cannot take any other value in the previous problem. Now in this problem, P itself is a random variable.
Variable P will have range 0.3 to 0.7.
What is the probability that?
Yes, probability. Both are equal. Both are less than equal to 1. There should be only one equality over.
P will lie between 0.3 and 0.7. Suppose you have made 10 tosses, you got 6 heads. Now from looking at this event, what can you say? What is the probability that the coin that you have tossed with has a probability between 0.3 and 0.7? That is the question which is asked.
The coin is unfair also.
Of course, because you are choosing a random coin and its probability can vary between 0 and 1. So we are supposed to find out probability of A given B. Now what is that? Obviously it will be the same thing. It will be probability of this will apply. It will be a probability of B given A into probability of A divided by probability of B. There is no doubt about that. Right. Now the question is, how do we evaluate these things? The evaluation is not that simple now. So first of all, let us find out what is the probability of B given P. If we are told that the coin that you have chosen has probability P, then what is the probability of B? It is Bernoulli trials. So it is 10 C6 P to the power 6 1 minus P to the power 4. This is the probability that there will be 6 heads. Probability of 6 heads is p to the power 6. They are all independent tosses, and probability of rest 4 is 1 minus p to the power 4, and you have 10c6 number of them, that is the heads and tails can occur in any order. So how many such arrangements are possible? Standard. So this is probability of B given P. So from this we can say that probability of B you can immediately calculate. Probability of B is nothing but 0 to 1, probability of 0 to 1 because Fp dp for all values of P. Now you are taking average, correct? See, what are you doing? You have to imagine. So probability is like, we have a frequency interpretation of probability. That is the interpretation which people used to give till this measure theory came up. So people used to say that if I do n number of tosses, how many times I get heads, how many times I get tail, ratio is probability. That used to be the interpretation that people used to give. So if you think in that way, what are you doing? You want to find out the probability that suppose there are n number of coins heaped together. So you are randomly taking one coin, doing very large number of tosses, then taking another coin, doing very large number of tosses, doing another coin. In this way, for each you are picking up a coin and you are doing a large number of tosses with that coin. So if you see just the probability of these tosses for each coin, then you get what you get here. Pick up any one and do a large number of tosses and see the ratio of heads and tails. That ratio is given by this. Now if you sum up, when you are saying probability of B, you are saying that now I will not sum up for a given coin, I will sum up over all coins. So then I will sum up over all the experiments that of coin picking also, right? Suppose if you do thousands of, for each coin if you do 1000 tosses, and if you pick 1000 coins, so now you will calculate this number of heads and tails over 10 to the power 6 number of tosses. So obviously now you will have to when you pick them up 1000 times, how many times, what will be the frequency of a given P coming up, that will be given by this FPDP naturally. So that's why you have to integrate. Are you getting the idea? So this is probability of B. Now the question is, what is probability of B given A? Probability of A is known. Probability of A is probability of the chosen coin has, see, this P is a random variable P uniform in the interval. So the probability of choosing a coin with this, where P lies between this, is simply 0.4.
So what is FP, sir?
What is FP is this. This is FP. This is P. 0 and 1. So suppose this is 1. So this is FP. Uniform in the interval 0 to 1. This is 0. This is FP. So this whole area is 1. So then between 0.3 and 0.7, say 0.3 is somewhere here, let us say, and 0.7 is somewhere here, let us say. So between 0.3 and 0.7 it is going to be 0.4 naturally. So PA is 0.4, there is no doubt about it. PB also now we can calculate, we can simply put this here. That is reasonably simple to do. Question is, tricky part is, what is P probability of B given A? This is the tricky part. Now the probability of B given A is not just this between 0.3 and 0.7. That is not correct. That is, you don't just change the integral limits here. Because now you are given that the coin has probability between 0.3 and 0.7. So now imagine that you have, somebody has now, from the big lump of coins which you had, the big heap, you have separated out, somebody has separated out only those coins which had 0.3 and 0.7 and then made a smaller heap. And then he is asking you that now why don't you do your tosses from this small heap and then find out what is probability of B. There is still uncertainty about P, because all coins in the heap does not have the same P, but it is now given to you that it is between 0.3 and 0.7. You have to choose from the smaller heap now. So if you have to do that now, obviously your probability density function will change, and what will it be? Now your probability density function, that is the f of B given A, is now different, or rather this is not f of B given A, this is f of P given A. What is the probability density function of P, but given that P lies between 0.3 and 0.7? This is only the ordinary probability density function of P, nothing is given, it could be anywhere. But now you are, what is the probability density function of P given that they all lie between 0.3 and 0.7? That is, if you can you characterize the probability density function of that small heap. So now it will be everywhere, so now it will exist only between 0.3 and 0.7 of P, everywhere else it will be 0, because you do not have any other coin. And since the whole thing is uniform, so here also it will be uniform, in any interval it will be uniform. So now this is going to be again like this, but this level will now be 2.5, because the area must come to 1. Correct? So this is your probability density function of P given A, right? So now if you want to find out probability of B given A, then you have to find out simply probability of B given P f of P given A P dP, this integral, and obviously since this is 0 everywhere else, so this integral you have to integrate between 0.3 and 0.7. This is equal to probability of B given A. Remember that when we did that longevity example, what did we find out? We said that what is the probability that if somebody is age is greater than 65, what is the expected value of his living, right? So we found that the expected value now lies between the remaining interval. People live between 0 to 100, so somebody has already lived 65, so his probability of living is again uniformly distributed between 65 and 80 and 100. So the mean came in the middle as 82.5. That's what we did in the class. So here also the same thing is happening. So now this is probability of B given A. Now you can do the problem. Probability of B given A is given. This one you know. This one is nothing but 2.5. This you know, and you have to integrate between 0.3 and 0.7. And probability of A is, what is probability of A? 0.4. So now you know all the terms. So you can find out. Is this clear? This is the way you apply Bayes' rule. Alright. Now we have another one. This is simple. Simpler, let us say. Show that if y is x square, that is, now we are defining a function of a random variable where x is an RV, fy such that fy of y given x is greater than or equal to 0 is this. What is uy? It is the unit step function, that is the function is 0 for all negative values and it is 1 for all positive values. Right? So, how do you do this? There are certain things that you have to note. First of all, you have to find out that, let us see some parts whether we can recognize them, why they have come. Firstly, why this uy has come? Why this unit step function should be there? Because y cannot be negative. So there is no question of, when you define as y is equal to x square, there is no question of getting a negative y for real x. Correct? So therefore the probability density of y must be 0 for all y less than 0. So that is immediately achieved when you have uy. So you write it only for positive values of y without indicating as such, and then you put this uy. So whatever, even if you put a y is equal to negative here, actually if you put y equal to negative you will get absurd results. But suppose this was, even if this was some other function, you can put y equal to negative, doesn't matter, this will still make it 0. So you don't have to specifically write that y positive or anything like that, just for that reason. So that's why they put uy, because y cannot be negative. Why this? What is fx0? Fx0 is the probability that x is less than 0. I mean, we are not bothering about those, those finicky, continuity condition, whether less than or equal to, let's ignore them. They are. So what is 1 minus fx0? It is the probability that x is greater than or equal to 0. So this part, we should recognize this. 1 minus fx0 is nothing but probability that x is greater than or equal to 0. So what are you having here? So if you multiply it this side, you are having fy, y given x greater than or equal to 0 into probability that x is greater than or equal to 0. If you multiply that, it is equivalent to prove that same thing is equal to fx of root y by 2 root y. Uy I am for the time being ignoring. It is the same. What is this? This is nothing but fy into y. This part will go now. Once you have multiplied it by probability, then it will be fy. Is it not? No. It will be fy and x greater than or equal to 0. Right or not? Right? Now anyway you have to consider x greater than or equal to 0 only, because x less than or equal to 0 will anyway go. So we are considering only positive values of x. So this condition is automatically satisfied. Now what is this? Remember that if we have a function gx, then its probability density function was what? It was fx by g dashed x. Remember? Is it not? So what is g dashed x here? G dashed x is 2y, rather 2x is equal to 2 of root y, and what is fx? Fx of x is equal to fx of just this is expressed in terms of y. Since on the left hand side you have y, the same thing is expressed in terms of y rather than in terms of x. So what is fx of x? It is written as fx of root y, and at the bottom you have twice x, that is written as twice of root y. Just simple application of the formula. only little bit twisted because of these terms. Understood? Okay. So this is also not. Now we have another one. First read the problem. Suppose x and y have joint density fxy, xy is characterized like this. So what is, how does it look like? Looks like this. So suppose this is 1, this is 2, this is 3. Similarly, this is 1. This is 2 and this is 3. This is the xy plane, okay? This is y, this is x. So 0, x, and x is between 0 and 2. So x is in this region. Y is between 0 and 1. So y is in this region. And twice y and x is less than or equal to twice y. So what is the x equal to twice y line? X equal to twice y line is here. Is it not? So, and what is x is greater than or equal to twice y, that is means it is in this region. So the area in which fxy is non-zero turns out to be this area. This is the area in which fxy is non-zero inside this triangle. Right? First agree to this. And the value is given as 1. That means it is uniformly distributed over this interval, over this area. And what is the area of the triangle? It is 1, half base into altitude. So it is 1. If it was anything, there has to be a corresponding scale factor, because overall probability must be 1. So this is tallying. So this is where you have fx. Now you are defining a function called z is equal to x plus y. So where is that function? That function is this line. And the z is equal to, this is the z is equal to x plus y line. This is actually the z is equal to 2 line. You can have various kinds of lines. For example, z is equal to 0 line will be this. This is the z is equal to 0 line. Similarly, this is the z is equal to 3 line. Right? Agreed. So now the question is, what is, we have to find out what is fz, right? So what is fz? Fz is dfz by dz, derivative of the distribution function. What is the derivative of the, what is fz? Probability that z is less than or equal to z, right. So, for example, if you are given small z is equal to 2, what is that probability? The probability will be this line, this area, because on this side z is less than or equal to 2. Now x and y can take values only in this triangle, they don't take values elsewhere. So the values of x and y which are possible to occur and which will make z less than 2, can you see these dots? Is it visible on the TV? So this is the area. For example, if you chose z is equal to 2, so fzz will be the area of this triangle, right. Now you have to, question is that you have to find out this area for an arbitrary z. That is the thing. So obviously you will find that if you obviously if z is less than 0, probability is going to be 0, because it exists only in this green triangle. That is why they have said that z must be either between 0 and 2 or between 2 and 3. That means z can be only between 0 and 3, it is 0 elsewhere. So below 0 there is no probability, beyond 3 also there is no probability. Rather beyond 3 fz is 0, but if you integrate capital Fz will become 1, correct. So now you have to find out that as you sweep z from 0 to 3, how does this density change? That is how the area inside the triangle sweeping is changed. That what is the rate of sweeping of the area inside the triangle? That is fz, right. Step by step you have to visualize. In fact, I mean nothing. I mean I did them yesterday evening, so I am just sort of loudly telling you what was my thinking process. These problems are not solved in the book. So now what you do? So now you find out, now you discover that the way the area changes from 0 to 2, as it sweeps from 0 to 2 is that is in this zone of z, the area increases in a given way, and in the from 2 to 3 you can see it from the picture itself, the area changes in a different way. Can you see that? That is why you have different fz's in the region 0 to 2 and 2 to 3. Now it is not difficult to find out how this area is swept. That is very simple. I mean, for example, we can do you want me to do one of them? We can do it. After all, suppose we take some point here, an arbitrary point, this one. Okay, find out what is this point. What is this point? It is in the intersection of this point. What is the coordinate of x? It is z, because z is equal to x plus y and y is 0. So this point is z. What is this point? This point is z minus 1. How z minus 1? It is z is equal to x plus y, it is on the intersection, and x is equal to twice y. So z is equal to 3y. So y is equal to z by 3. So this is y. So this is z by 3. So this is z by 3, right? So then what is the area of this triangle? This triangle, it is half into z by 3, that is equal to z square by 6. Now that is equal to fz of z when z lies between 0 and 2. So now what is dfz dz? Z by 3. True. So, it is not all that difficult once you nicely draw a diagram and see what is happening. And I am trying to encourage you to try myself. Actually, you know, my trying, I mean, it has given me a lot of pleasure yesterday evening. I really enjoyed doing this, but because we don't get that much chance to do these things nowadays. So, I had a really enjoyable evening, but then that is of no concern to you. I am trying to encourage you to try yourself, and I mean not be intimidated by this, you know. I mean the moment you see this, I mean it hits you, I mean you feel that, oh Baba, what is this? It is not all that difficult. Okay. So, now probably you can try the other one, which is a little more tricky. Nothing tricky, I mean the expression is a little more. I did that expression also, and it is coming, it is tallying with what is shown, so it works out, but maybe you can try yourself. Okay, this is very simple. I mean it's a one liner actually, if you realize what is happening. So, read the problem. So, it says that Gx is a monotone increasing function. This monotone increasing function, as we discussed yesterday, we were discussing with some students, and this monotone increasing function is important, because that means that for every value of y you have a value of x, and the function can be inverted, etc. If you have a monotone non-decreasing, I mean the moment you have a function such that many values of x give one value of y, you have problems because you cannot invert the function. You understand? So there are problems. So, but when you have a monotone increasing function, then you have one value of x for one value of y, because it is all the time increasing. If the function x to y was like this, then here you have a problem, because for many values of x you have one value of y. You cannot invert this function. But if it is going like this, then for every value of x you have one value of y. So, I mean that way monotone increasing and monotone decreasing functions do not pose problem. So, this is told just to, you know, so that some technical difficulties are avoided. You can forget about it. Just imagine that y equal to gx. Now the question is, now read this. What is fxy? You have to always go back to definitions when confusion. Is what? It is the probability that x is less than or equal to x and y is less than or equal to y. Is it not? Now the point is that if x is less than or equal to x, then necessarily y is less than or equal to gx. Is it not? Because it is a monotone increasing function. It is a monotone increasing function. So, if x is below small x, then y will be below gx. If it was a decreasing function, it would have been greater than or equal to. That is why this monotone increasing function is needed. Agreed? But the problem is, now the question is that, now suppose, what is this saying? This is saying that if y is greater than gx, you have chosen a y. Now the point is that, can it happen that x is less than or equal to x and y is less than or equal to y, where y is greater than gx? if x is less than or equal to x, y must be less than or equal to gx, because they are related like this, rather because they are related like this. So if you have, suppose gx appears to be 2, so you are saying that, suppose just imagine that gx is equal to 2x. So you are saying that what is the probability that x is less than or equal to 1 and y is less than or equal to 3. It cannot happen that y is less than or equal to 3. So basically y is less than or equal to 2. You are just artificially putting that value 3. If x is less than or equal to 1, then y cannot go beyond 2. So even if you are putting a value 3, between 2 to 3 you will not get any value of y. It's as simple as that. So that's why when y is greater than gx, only this x limit applies. So the y limit will not apply, because y is determined by x. And if you are putting a value of small y which is beyond that, then in that range between gx and y you will not get any value of y. So that part you need not consider. Are you following what I am saying? Similarly, now if you have artificially chosen y less than gx, that is, you are saying that what is the probability that x is less than or equal to 1 and y is less than or equal to 1.5. So if y has to be less than or equal to 1.5, then x has to be less than or equal to 0.75. X cannot be greater than 0.75. So then you have to restrict the range of x, and it is the range of y which will be effective. You understand? So if y is less than gx, then it is the range of, it is the probability distribution of y which will be dominating. Are you following? It's just simple. I mean, there is nothing in it. I mean, you don't have to do anything. It just looks, they will say monotone increasing, just to impress you. I mean, it has a meaning, not just to impress you, but I mean that puts you off. What is monotone increasing? That sort of thing happens. So just fight it. That's what I am trying to say. Okay, we have, this is a very simple problem, and a very common problem too. I mean, this shows that this. So we'll close with this one. So it says that, suppose you have a population, of random variables. So somebody has performed 20,000 experiments and have determined that its expected value is mu and its variance is sigma square. It is a value which is, now the point is that every day if you want to find out what is the mean value and things like that, you can't do 20,000 experiments. So you typically, what we tend to do is we take few samples and then take an average. Just simply evaluate this. So this is called a sample mean. This is called a distribution mean, and this is called a sample mean. So here what we are doing is excuse me, we are generally taking n samples. N is a finite number, 10, 20, 30, 100, whatever, depending on the time and money that you can spend, and averaging it, simply 1 by n. And we are many times using that as the mean. Now it turns out that it is not the mean. It is also a random variable. After all, you have taken capital N number of random variables and you have summed them up, so it becomes another random variable. Now the question is that, is it a good, that is, if you consider this to be an estimate of the mean, is it a good estimate? So how do you find out whether it is a good estimate or not? At least on an average, if you found out 10,000 such means, then took their average, then does it converge to the actual mean? That is a measure of its estimator. If it turns out that this estimator will be always 0.1 away from the mean, irrespective of the number of trials you make, then it's not a good estimator. I mean error does not increase with effort. So the question is, does it happen? So one way of finding that out is to find out the variance and the mean of this random variable. This is a derived random variable. So what is the mean and the variance of this random variable? That is very simple to find. For example, you can easily find out that what is the expectation of mu hat n? It is nothing but expectation of 1 by n, just putting I is equal to 1 to n xi. So put expectation, take it, this is a finite sum, you can easily take expectation inside, there is no question of limits not converging, etc. So it is 1 by n sigma I is equal to 1 to n expectation of xi. Expectation of xi is already given as mu, so it is mu. So it turns out that the expectation of this random variable at least matches with the distribution. Such estimators are called unbiased estimators. So that is one good thing. Now you will ask that, okay, mean matching does not have much value. If the variance is very large, then in a given experiment the value can be way ahead from the mean. So you not only want that on an average it matches with the mean, you also want the variance to be small, then it is a good estimator, right. So it is a very legitimate, so we can try to find out what is the variance of this estimate, and it will be good if we find that this variance decreases as we increase this n. So if we take larger and larger number of averages, then it is more likely that it will come closer and closer to the mean, to the true mean of the distribution. Does it happen? It will happen, and you can easily just put the formula. So what is the variance of mu hat n? It is expectation of mu hat n minus expectation of, just simply blindly put the formula, whole square. This is the formula of variance. This you have already calculated. Expand this, put in place of this you put this, so it becomes an a plus b plus c plus d plus e, it becomes a sum whole square. So you know what it is, expand it, a square plus b square plus c square plus d square minus twice ab 2bc, all terms open up, then take expectation. You should get that this is equal to sigma square by n. That is good, because it is saying that if you consider 3 samples and you will get some variance, if you take 30 samples and then do this average, see you are putting more effort, so you should get a better estimate, and it is indeed better because this will be reduced. So if you get a 30 sample average, then you are likely to be closer to the true mean every time on an average than if you take a 3 sample mean. That is what it means, which is true, right. So we have seen some, my talk is over, we will again see in the evening. I hope you will come up with some other problems, but only hope that this clarified some